Okay, so what I want to do today, I want to do a couple things. It's going to be an ambitious day. I want to introduce the concept of a matrix to you, and I know some of you may have had, probably in chemistry, is that where you maybe have seen these a little bit? Some of you have seen matrices, maybe just, raise your hand if you've ever seen a matrix before. Okay, a couple people, a handful of people have seen them. They're going to be new to many of you. I want to introduce you to what a matrix is, the definition of a matrix. Lights on or off? What's better? Can you see that better if I do that? Yeah. Okay. Introduce you to what a matrix is, and then we're going to talk today about how you can do arithmetic with matrices. So, what is a matrix? Okay, a matrix it's just a collection of numbers, is really all it is. Not necessarily even numbers, collection of elements. They could be numbers, they could be variables. Looks sort of like this. The matrices that we're going to see, and this is pretty standard, the matrices we're going to see they're going to look something like this. Instead of having the square brackets, they're going to look like that. So for example, we might see a matrix, thank you. Jennifer Houlihan, is she here? Not here. Whoops. She's actually here. Jennifer's not here. Okay, thanks. So ours are going to they're going to have these rounded brackets, the ones that you see on Moodle, and they might look like this. Okay, that's an example of the kind of stuff we're going to see. So a matrix, anyway, it's a collection of these elements, and we divide a matrix up into rows and columns. You know, pretty obvious. The rows are going to be the horizontal collection of elements. There's row 1, there's row 2. And then column 1 and column 2, etc. And when we want to define the elements of a matrix, we always give them two numbers, two subscripts. So I would say that this is A sub 1, 1, or A 1, 1, and really what that means is row 1, column 1. Okay, that's all that's saying. This is row 2, column 3, and so we call it element 2, 3. Make sense? Okay, so that's how we keep track of the parts of a matrix. Okay. All right, so there's our rows. Now, when we want to define a matrix of indeterminate size, we just want to do kind of a general, all-purpose, generic matrix. We might say that it's got m rows. M could be anything. It might be 7, it might be 100, it might be 2. But this is, so we've got row 1, row 2, row 3. These dots just indicate, and then there's going to be potentially a bunch of other rows. Last row is row m. These are our columns. Column 1, column 2, column 3, etc. And if it's generic, we might say that it goes all the way out to, well, in this case, column 4, but we might even say it's just like column n. Yes, ma'am?
So like row 1, row first.
Yes, exactly. So notice that. Exactly. So when you look at these numbers, the first number is the row number and the second number is the column number. Okay? That makes sense? Whenever we talk about the size of a matrix or an element in a matrix, we always do rows first and then columns, R before C. And the way I remember that, you probably have never even seen this before. I don't think they have it in Oregon anymore, but there's like Coke and Pepsi, and then there's this other cola called RC Cola. And so RC, that's how I remember, RC Cola, R before C. Yes, ma'am?
So, will the variables always be the same?
Meaning the A, will it be an A?
Like, will it always be the same? Not like A, but like.
Okay, yeah, these aren't variables. This is just, when you see something like A is just, typically in a matrix, this would be what we call matrix A, which is like a template for a matrix. And then all of the elements in here, we call them A when we don't know what they are. So usually, an example would be something like this. If we had, and this will make more sense once we get into it more, but let's say we had something like this. If we have matrix A something like that, then that's just saying that element 2, 2, so row 2, column 2 entry is 4. Okay? That's kind of all we're saying is this is just some generic matrix. If we actually populate it with numbers, then what is A 2, 2? In this case, it's 4, because the row 2, column 2 entry is 4. Okay, so typically we're going to see matrices that don't have stuff like this in there. They're going to have actual numbers in them. Okay? Okay. So if it's m rows and n columns, then we would say that that is an m by n matrix. We always do the rows first and then the columns. Okay? So for example, what are the dimensions of this matrix? It's a 2 by 3, right? Because it's got 2 rows and 3 columns, right? So that's a 2 by 3. What's that one going to be? 3 by 3. Okay. Make sense? 3 rows, 3 columns. What's that one? 2 by, that's a 2 by 1, isn't it? 2 rows, 1 column. What's that one? 1 by 2. And what's, oh, I guess we didn't get it in there. I thought there was going to be one more. Okay. Well, I mean, this get cut for you guys. What's that, real quick? 3 by 2. What's that? 2 by 2. What's that? Good. 1 by 2. 2 by 1. What's that? 1 by 1. There you go. Pretty boring. Okay. So addition and subtraction of matrices. Okay, to add matrices, we just add the corresponding elements. Okay. So therefore, if we're going to add matrices, for us to be able to do that, the matrices have to look the same, don't they? They have to be of the same dimension. So I could add those two. Matrix A plus matrix B would be what then? It's going to be what's the dimension, what are the dimensions going to be of that sum? 2 by 2, because I started with a 2 by 2 plus a 2 by 2. And does it just make sense then that I'm going to get for the row 1, column 1 entry is going to be -5 plus 6, so it's 1, right? 0 plus -3 is going to be -3, etc. Pretty straightforward. Adding matrices is really simple. Okay, if I add, this is called the 0 matrix, where all the elements are 0. And so what I want you to, this is pretty boring, obvious stuff, but what I want you to see about this is that adding a 0 matrix is like the matrix equivalent of adding a 0 number to something, right? What I want you to kind of try to capture in your mind here now is a connection between matrices and real numbers, because they act in much the same way, and that's a great way to think about it. So even though this is a big collection of individual numbers, it's like the matrix equivalent of a real number. Yes, ma'am? Question?
Where, like, what are matrices, like, where do you find?
Okay, what are they good for? Yeah, is that what you're asking? What are they good for? Matrices are very useful because they contain a lot of information. And so like a matrix, a 3 by 3 matrix, it's got 9 different elements in it. So it's got the ability to contain a lot of different information at once. A lot of times what matrices correspond to in the real world, matrices correspond to vectors. And so like, for example, a vector is, you guys, you're not going to be real familiar with vectors, but this is, this is worth mentioning. This is a good question. There are 2 kinds of quantities that we like to talk about in math and in physics, vectors and scalars. Scalars are quantities that a number is all you need. Like, what's the temperature of the room? Well, it's 70 degrees. That's a scalar quantity. What page are you on in your book? That's a scalar quantity. All you need is a number. Vectors are quantities that are more complicated. Vectors require more than one number taken together. In other words, they require both a number and maybe a direction. Okay, so for example, if I wanted to pinpoint where is my finger in the room, now that's difficult to do. There are some numbers required because that's going to be a different place than this place is. But we also have to have some direction associated with it. So relative to, let's just say that this is going to be the anchor point that we're going to measure all distance or all position from, then where's my finger now? Well, it's from there to there is a certain distance, but it's also a very specific direction, right? To make that regular and understandable, we usually, we live in a three-dimensional, three-extended dimensional universe, and so what we would do is we'd break that up into components. We'd say, okay, in the x direction, to get from there to my finger, we're going to slide right by a certain amount, we're going to go up by a certain amount, and then we're going to come out of the board a little bit. Remember, we kind of talked about that stuff, right? And so we give it a vector that has three numbers associated with it. And so when you start to collect those things up, you start to get lots of numbers. We're going to get an x component, a y component, a z component for all those numbers. That's where matrices start to be really useful, because the operations that we can do with matrices will really quickly allow us to take these collections of numbers and do calculations with them. See, with matrices, we're not going to get into a huge detail about how to do operations with matrices, but those of you who go on, and I'm hoping this is everybody, and take substantially more math in college, you will take a class called Linear Algebra and Matrix Theory, and it's going to talk about how you can deal with what are the tricks when you have a collection of these numbers in a matrix. How can you do math with it? There's things called row operations you can do where you can recombine the numbers and do this and that, and real quickly you can turn a matrix into an answer using those operations. Now for us, and honestly what you do in the real world now when you're dealing with matrices is you do all those row operations on a calculator. You just input the matrices on a calculator and let the calculator very quickly do all the matrix arithmetic for you and spit out an answer. But you still have to understand how to set that up, how to input the matrices into the calculator even, right? And that's as far as we're going to go with it. But that's what they do. I mean, they really do important stuff. You can use a lot of detailed information, put it in a matrix, and it'll spit out a single number very quickly.
You said that they act like they could be real numbers.
Yeah, they do, exactly.
What do you mean they could act as real numbers?
Well, okay, so what I mean here is, if we were to compare this to a real number situation, matrices are a lot more complex. They contain a lot more information, but this would be just like the number equivalent of saying 7 plus 0 equals what? 7. Now that's important because that 0 is our identity number for addition. And so the important thing we had to notice there is that anything plus 0 equals itself. For matrices, any matrix plus a 0 matrix will always equal itself, right? And so there's an analog, there's a real number analog to that too. The matrix version is a lot richer because there's a lot more information contained, but it follows a similar pattern and relationship. Does that make sense? Okay, so that's kind of what I'm getting at there. A lot of this is just setting you up to be familiar with the concept of matrices and matrix arithmetic down the road in college when you do more with it. Yes, sir?
Are we gonna have to deal with like equations in matrices, like x
Yeah.
and y?
Yeah, a little bit. Yeah, but it's no big deal. We'll do some limited stuff with that. Yeah. So we get the original back, right? So anytime we add a 0 matrix, we get the original back. So that's our 0. That's our identity matrix for addition. Okay, it's a 0 matrix. To subtract matrices, what do you think you do? It's exactly what you'd expect. If I subtract those two matrices, what am I going to get for my row 1, column 1 element? 0, sure, because it's just going to be 1 minus 1, right? Make sense? And so over here I'd get for the row 1, column 2, I'd get 2 minus negative 1 is 2 plus 1 is 3, right? Et cetera, right? So if we keep moving on here, you know, I mean, you know how to do that. I'm not going to belabor this point too much. You guys can, you'll have no problem adding and subtracting matrices. And I'm going to ask you to do a little bit of that without your calculators. But very quickly, you're going to do a lot of this stuff on your calculator. So how do we do this on a calculator? How do you enter matrices and do arithmetic with matrices? Let me introduce you to that right away. So I'm going to pull up the calculator. How about? And why don't I can't. Kind of gets in the way a little bit, doesn't it? So to add matrices, here I'm going to go back. Let's just go back to like those two. Okay, if I wanted to add those matrices on the calculator, here's how you do it. Okay, everything happens in the matrix screen. So you go second. And just so you know, when these videos show up, I think the ones with calculators are particularly useful. If you want to see the buttons I'm pushing, you probably noticed this, but they always turn red. So you can keep track of the buttons I'm pushing just by watching, you know, which one turns red. So second matrix gets you to the matrix screen. Okay. Right? Now notice there are several different menus on here. We're going to use all of these. When you go to the matrix screen, you've got the names menu, and that just tells you if I want to use a matrix to do something, to do some arithmetic, that's where I can sort of grab the matrix to do something with it. Okay? If I want to define a matrix, I want to build a matrix, I have to go to edit, of course. So I'm going to hit the left arrow to cheat and scoot over to the edit menu. And I'm going to hit enter then on the first one, or 1, to pull up matrix A and build it. Okay? So in this case, notice what you do always. Matrix A, first I have to tell the calculator what the dimensions are. So what should the dimensions of matrix A be? That'll be my first one. 2 by 2, right? So we're going to call this one, matrix A, and we'll call this one matrix B. Good, so it's going to be a 2 by 2. So 2, enter, scoots me over, 2, builds a 2 by 2 matrix. Yes, ma'am?
How did you get to matrix A?
Matrix A, you just go second, matrix, so I'll do that again.
Yeah.
Second, matrix, and then I scoot over to the edit column. So I scoot over to edit, and then it's on matrix A, so I hit enter, and it gets me to there. Okay? So I entered a 2 by 2, and now all I have to do is just add the elements. When you hit enter, it reads like a book. You go left to right through the column, and then it'll skip down to the next column. So I would just, for this one, go 4, enter, negative 1, enter, and it pops me down to the next row, 6, enter, negative 3, enter. I've got that one built. Okay, it's in the hopper. It's stored in my calculator. So now to build matrix B, where would I go? Second matrix. I got to go over to edit, right? So scoot over to edit, and I either hit the down arrow or I just type a 2 to get me to matrix B. So that needs to also be a 2, enter, and that's already a 2, so I'll just hit enter. And then I'll just populate it with these elements. So negative 6, enter, negative 5, enter, 7, enter, 3, enter. And now I've got matrix B. And so if I want to do something, I'm going to quit, get out of there completely. If I want to do something like add matrices A and B, I just go second matrix to the names menu, and grab matrix A, plus second matrix, and I got to grab matrix B, so I just type a 2, right? If I hit enter, look what it does. Adds them up. Question?
How'd you get the second one?
This-
After like finishing the first one, how'd you get to
Oh, the second one, as soon as I finished the first one, I just went second, matrix, edit, and I went to number 2 and built it. Okay? Now what's nice about that is, once I enter the matrices, I can do any kind of operation I want, right? If I want to, and check this out, if I want to go back, this is kind of cool too. You guys are going to get really good with these calculators. Let's say I added A and B and I decided, oh no, I really wanted to subtract them. Well, I could just do A minus B, or I could even go up here and highlight that and grab it, and look what it does. It pulls it down for me to change. So now I can go over with my left arrow and overwrite that and turn it into a minus sign and hit enter, and it subtracts them. Right? How did it say it again?
Say cool.
Okay, so I'm at matrix. How do you get back?
Quit. Second quit. Gets you back to the home screen. Okay? And then you'd go matrix 1 plus matrix 2 gives you A plus B. Does that make sense? Okay, and then if I wanted to, I could multiply them too. Now, we don't know how to do that yet, but I can multiply those matrices too. Okay, so if I go grab that operation row, edit it, I'm going to turn that into a multiplication sign, and that gives me a weird answer too. Now, we got to talk about how to do that next, how we multiply matrices. But are we all okay with being able to enter a matrix on the calculator and add or subtract it at this point?
Yeah.
Yeah. Okay. All right. So I'm gonna put the calculator away for a moment then, and zip through this. And so I'll leave that up for a second so you can. There's a list of directions that you can get to. I'll put this under the resources for Unit 3 also, but now it's included in the YouTube video. You can just pause it there if you want to. Print that screen if you wanted to. So scalar multiplication. Okay, this is easy multiplication. Scalar multiplication is what we get if we multiply a matrix by some constant. Okay, by something. I'm multiplying the whole matrix through by k. What do you think you do in this case?
Multiply each other by k.
Yeah, we just distribute the k through to all the elements in the matrix. That's it. Okay? And your calculator knows how to do that. Your calculator knows how to do all this stuff. If I were on my calculator to, if I were to try, for example, I'll just show you here real quick. This is kind of cool.
Can you show me how to do it?
No, can't show you how, but I could do something like this. I could say 4 times second matrix 1. So 4 times A is that, right? Just multiply everything by 4. Okay? Okay, and this is, we'll just, for you guys, oh, and it's no different with variables, right? If I've got variables in my matrix, I would just distribute this 5 through to all the parts, and so here I'd get a 5y, there I'd get a 5x, there I'd get a 5x squared. That's
Just like expansion.
yeah, it's nothing any different.
Distribution.
Okay, there's an example, scalar multiplication, but that's no big deal. You know how to do that. Okay, so what about solving a matrix equation? Now this is kind of interesting. How would we do something like this? Now there are, if you happen to have a TI-89, you could actually have it do this whole problem for you and solve for x and y. Yours won't. Yours won't because yours won't do symbolic algebra. So this is a case where you'd actually have to do something like this by hand. Yes, sir?
What about like Inspire?
Yeah, we do it too.
Okay.
But this is no big deal. How would I go about solving for these variables? Any ideas?
We'll just add them.
Okay, good. I could go through the matrix arithmetic here, couldn't I? I could combine these matrices and eventually I've got to get a 2 by 2 matrix on the left equals a 2 by 2 matrix on the right. And if two matrices are equal, what does that say about the corresponding elements? If the matrices are the same, don't all the parts have to be the same? You start to see maybe a way where we could set up, where we could solve for x and y. If I combine this stuff, we're going to simplify the matrix. I could just add this, if by order of operations. First I work inside the parentheses, right? So I'd add up those two matrices and get something like this, right? 3x plus 4, -1 plus 1, etc. Okay, so I get that. Now what? Okay, I'll do the scalar multiplication. I'll distribute the 2 all the way through and get that. And now what? Notice that the 0 is equal to the 0, the 12, and the 12. Those have to be the same if the matrices are equal. How could I solve for x? What do you think?
Just do 6x plus 8 equals 26.
Yeah, good. I'll just set the corresponding elements equal to each other, right? So row 1, column 1 elements have to be equal. So I get the individual equations. 6x plus 8 equals 26, and 10 minus 2y equals 8. And those are pretty easy equations to solve, right? So that's how I could actually solve that matrix equation for the individual variables. Okay? All right. So properties of matrix operations. Okay, I mentioned, and this is really important, I mentioned that matrices, we want to be able to think about them like real numbers. The matrices are doing the same kinds of things that we do with numbers, only a little bit more involved and complex. There's some things that are true for matrices, just like they're true for real numbers. The addition of matrices is associative. So I can add matrices. If I have 3 matrices that I'm adding up, I can add them in any order. Doesn't matter. Okay? I can group them as I wish. Matrix addition is commutative. Matrix A plus matrix B is equal to matrix B plus matrix A. And it's distributive. Now there's something important about the distribution though. This is really important, and we'll get into this more later. Matrix distribution, the direction is important with matrix distribution. So if I'm distributing matrix S over the sum of matrices A and B, matrix S has to be multiplied by A from the left, and S has to be multiplied by B from the left if I'm distributing from the left. Okay, so distributing from the left and the right is different for matrices because multiplication does not have these same properties. That's the key. And you're going to see this shortly. Multiplying matrices, multiplication of matrices is not associative, and it is not commutative. That's strange. It's very different than real numbers. 3 times 4, of course, is the same thing as 4 times 3. Matrix A times matrix B is not the same thing as matrix B times matrix A. You'll get different answers, and in many cases, one will work and the other will not. And that'll be really obvious to you why that's the case very shortly. So let's look at multiplying matrices. So in order to, I got kind of messed up. In order to multiply matrices, here's the thing that's kind of strange. The first thing that's kind of strange. When you multiply matrices, the dimensions of the matrices don't in general have to be the same. Typically, they're not going to be the same unless they're square matrices, and then they will be. But if they're not square matrices, if matrix A has a different number of rows than columns, then matrix B is not going to be of the same dimensions. What's important is that when I line up the dimensions, the inside dimensions have to match up. So think what that implies then. The number of columns in the first matrix has to match the number of rows in the second matrix that's being multiplied. That's a little strange. Yes, sir?
So why can't they be like rectangles being the same?
You'll see. It doesn't work. You'll see why here in a second. It doesn't work that way. Okay, and then the dimensions of the product matrix that you get after you multiply are always going to be the outer dimensions of the product. Okay, so let's look at some examples. Could we multiply a 2 by 3 times a 3 by 4? Yeah. Yes, we could, because the inner dimensions match up. The 3's match up. What's the dimension of the product matrix gonna be? 2 by 4. Okay, that works and you get a 2 by 4. Can you multiply a 5 by 3 times a 5 by 2? No, you can't, because the 3 and the 5 don't match up. Okay, so that won't work. It's not possible. How do we multiply matrices? If I want to multiply this 2 by 1 times this 1 by 2, first of all, is it going to work? It is, isn't it? What am I going to get back for my resultant matrix, my product matrix? A 2 by 2. Okay, now how do we go about doing that? Here's what the answer is. Question?
Yeah. So, if the inside dimensions didn't match up, but the outside state, could you flip A and B?
No. Well, yeah, you could multiply them in the other order. It's a good question. Does everyone understand Trenton's question? Good question. He said, what if matrix A is a 2 by 3 and matrix B is a 2,
There's a 3 by 2 here.
By 2,
is a
3 by 2, 4 by 2.
Apple.
how about if it's a 2 by 4? That's not gonna work either,
Because
is
it
it?
would be
No,
row,
no.
row, row.
The 2 has to be on the outside.
Yeah, so if it's a 4 by 2. Yeah, there we go. That's the question. I got you. It's a 4 by 2. Okay, those don't multiply, do they? Right. Those don't multiply, but, so A times B is not defined. But B times A would be a 4 by 2 times a 2 by 3, and that would work. So if I multiplied them in the other order, they would multiply. Okay? So how do we do this? Here's what we do. We multiply the row of the first row of the first matrix by the first column of the second matrix. Okay? So the first entry here in this case is going to be A times C. That's going to be the row 1, column 1 element of the product matrix. So we're taking row 1, column 1 to get row 1, column 1. Okay? To get row 1, column 2, we multiply in this case A times D. Okay? To get row 2, column 1, we multiply row 1 of the first matrix times column 1 of the second matrix. And of course, to get row 2, column 2, we multiply B times D. Okay? Yes?
So kind of like implying it square in biology.
I mean, it's going to have some analogs, yeah. But here's where it's going to get a little weirder. Where it gets a little weirder is if the inside dimensions aren't 1. Okay, what happens in the case where we've got something here? I'm going to skip through this. What about this guy? Okay, what if we want to multiply? I don't know why this worked out to be so, the graphics aren't working. What if I want to multiply a 2 by 2 times a 2 by 2? Now that multiplies, doesn't it? The inside dimensions are the same. How does that work here, though? Well, this time, here's how you have to kind of visualize this. This time, I'm going to multiply row 1 times column 1. And we're just going to stack up the corresponding elements of those rows and columns are going to get multiplied. So we're going to walk down the rows from left to right and the columns from top to bottom. And every time we get to a new element, we'll take that product. So the 4 matches up with the negative 4, right? So we're going to multiply 4 times negative 4 plus 1 times 1, right? It's a little strange. So it looks like that. Okay, we get the answer negative 16 plus 1. That's going to be the,
Why does it change from the first?
because now we've got, the first time we only had one Remember, the first one was a column matrix. It was a 2 by 1, and the second one was a 1 by 2. And so when we superimpose these, we only had one element in the first row and one element in the second column, right? Or in the first column of the second matrix. But now we've got a row that has more than one part to it. It's got two parts. It's got two elements. So the first row of the first matrix has two elements. The first column of the second matrix has two elements. And so how do I do that? How do I multiply that collection of two numbers times that collection of two numbers? Well, we just do it we do it in corresponding orders. So we go from left to right along the first column. So there's the first number, we'd say. There's the second number of the row. Here's the first number and the second number of the column. And so we just multiply those in pairs and take the sum of all those little mini products. So what about over here then? Well, this is the row 1, column 2 product, right? And so I'd have to take the product now of row 1 of matrix A and column 2 of matrix B. So that's going to be 4 times negative 3 plus 1 times 2, right? So it's going to be negative 12 plus 2. Okay, make sense? Okay, if I want to find the row 2, column 1 product, then I've got to superimpose, of course, row 2 with column 1. So what's the first product going to be that I'm adding up? Yeah, so 0 times negative 4, right? Plus negative 2 times 1. Okay? Okay, what about for the row 2, column 2 product? That's going to be what?
0 minus 4.
Okay, 0 times negative 3, good, plus negative 2 times positive 2. Okay, and then I just, simplify that. And so there's my product matrix. Okay, see how that works? Does it make sense now? Why, now maybe you get a little insight. Now you can see why the number of columns in the first matrix has to match up with the number of rows in the second matrix, right? Because when I'm doing this superpositions thing, I'm taking these little mini products, I have to have the same number of elements in each row of the first matrix as I have in each column of the second matrix. Well, how many elements am I going to have in each row of the first matrix? The number of columns that the first matrix has, right? How many elements am I going to have in each column of the second matrix? However many rows that second matrix has, right? So the number of columns in this matrix has to match up with the number of rows in this matrix, or it wouldn't work, right? I'd have leftovers someplace that it didn't match up. Okay? Okay, does that make sense? How that works? I'm gonna skip through this. What I want to show you then is here's kind of a graphic on this. This is probably maybe what I should have showed you first. Maybe I want to flip the slides around. So if I want to multiply, first of all, are these going to multiply? Do the dimensions match? They do, don't they? I've got a 2 by 3 times a 3 by 2. What's my product matrix? What are the dimensions going to be? 2 by 2. So the first, now if you wanted to think what that first entry is going to look like, because look at the dimensions. We get a 2 by 3 times a 3 by 2, and we always know that whatever the outer dimensions are, that's the dimension of the product matrix. Okay? And that makes sense, doesn't it? Because we're going to take first row by first column, first row by second column, second row by first column, second row by second. I only get 4 products out of that, right? Okay, so that first one, that's gonna be the superposition of row 1 and column 1. And so it's gonna look like A times G plus B times I plus C times K. Make sense? Everybody see that? Okay. Row 1, column 2 is A times H plus B times J plus C times M, right? Everybody see that?
Yeah, I see that.
Row 2, column 1, D times G, right? Plus E times I plus F times K. You get the idea?
Yeah.
Right? And then, etc. So multiplying, you can start to see that even multiplying matrices by hand kind of starts to get a little bit tedious, doesn't it? There's a lot of individual elements to multiply there. Calculators do this very quickly. That's nice. Okay, so we'll skip through the, I mean, you guys don't need to see more probably individual examples. I'll put the PowerPoint up too, of course, so you'll have, you can click through any of these that you want to. But you get the idea, okay? Okay, I'll check some here. I think, is there one more thing? I'm trying to remember. Yeah, then I wanted to just pause on this. There's this slide that kind of, those are the steps you'd go through to enter the matrices and multiply, but you already know that. I mean, it's no different than adding them. The only difference is you're just going to put a multiplication sign in between.
Is division just like the exact same thing?
No, division is much, much more complicated. In fact, you really can't divide matrices in the same way you divide numbers, but we'll get to that later. I don't want to even start to tackle that one today. So how are we doing here? Do we have any time?
We're at 4 minutes.
4 minutes, okay. So.
I mean,